How do you debug or fix a circuit when it doesn't work? This is something that a lot of students find very challenging when they are starting out with electronics because it is not always immediately obvious and you can't necessarily see what is wrong or why the circuit isn't working. So this video is a follow-up to my series on how to build a circuit on a physical breadboard based on a circuit diagram. So say you have followed the diagram and you think you've checked all the connections, but you go to turn the circuit on or run your code and the circuit doesn't do what you expect. How do you systematically step through, double check the diagram, and figure out what is wrong with the circuit? In this video, we're going to go through each of the 5 examples from the previous videos in this series, which you can find linked in the description below this one. I am going to intentionally make at least one thing wrong in each circuit, ask you to pause the video and see if you can spot the mistakes, and then unpause and I will explain the errors. So let's get started with our first example of a simple circuit that just has a battery, a resistor, and an LED all in series. When I run this simulation in Tinkercad and turn the circuit on, I would expect the LED to light up. However, you can see when I run the simulation, nothing happens. So I am going to zoom in on the breadboard a bit here and ask you to pause the video here, look at the breadboard, and see if you can figure out what is wrong. No cheating. Pause the video if you haven't paused it already. So, could you spot the error? The highlighting in Tinkercad here might give this away. This is a common mistake when using a breadboard and trying to physically orient parts such that they are in the same physical arrangement as they appear in the circuit diagram. So, in the diagram, I have the resistor in series with the LED, and it looks like I have put the resistor in series with the LED physically here. However, remember, this is not how holes in a breadboard are connected. Holes are connected across each row. They are not connected across the columns or between adjacent rows. So even though it looks like my resistor is in series with the LED here, these two rows are not connected. There is no connection between actually any of these components. This wire, the LED to the resistor, or the resistor to this wire. This is just a bunch of open circuits. So if I want to actually have a closed circuit here, I need to move these components so they are in the same row and have an electrical connection. So I'm going to move this wire down here, this wire up here. Now I have a path for current to flow, and when I run the simulation, my LED is going to turn on. So again, common mistake when using a breadboard, forgetting how the holes in the rows are connected but not connected across columns or jumping between the rows. All right, let's kick the complexity up a notch and go to our second example circuit, where we now have 4 LEDs with their current limiting resistors in parallel branches. One of them has a button in series, and there is now a switch in series with the battery pack to control power to the entire circuit. So what I would expect to happen based on the diagram when I run this simulation is that if I close this switch, 3 of the LEDs will turn on, and the 4th LED will not turn on unless I push this button. However, you can see when I start the simulation, nothing turns on. So again, there is at least one thing wrong with this circuit diagram. I'm going to zoom in a bit so you can see it here. Pause the video and see if you can spot one or more mistakes that are causing this circuit to not work properly. Okay, so there is more than one thing wrong here. Let's go through them, not necessarily in order. One, and this might seem obvious, but I have certainly forgotten to do it on many occasions. I forgot to fully connect my power. There's no ground wire to my battery pack, and you need a closed circuit for current flow, so just connecting one wire is not going to do anything. So I'm going to stop my simulation, go ahead and connect the ground wire from my battery pack. Again, you might think that's obvious, but it is really easy just to forget to plug the thing in. So I'm going to go ahead and run my simulation now, and I would expect everything but the yellow LED to turn on and the yellow LED to be off until I push this button. So let's see, my master switch does appear to be working, and that turns everything off, but turning it on, something's wrong. My red LED is not on at all, my green LED is dim, blue LED appears to be working, but the yellow one should be responding to this button, and the button is not doing anything. So clearly there is some other stuff wrong here. Let's take this top to bottom. Red LED, look closely. Whoops, resistor's in the wrong row. So just like we saw in the previous circuit, this is an easy mistake to make, even if you understand how a breadboard works and did know that this needs to be in the same row as the LED. Tinkercad has this nice zoom feature where I can zoom in real close and see that clearly, but especially as you're building a more complex circuit, and in real life these holes are at a 1/10 of an inch spacing, so they're pretty tiny. It can kind of just look like things are together, but it's actually off by 1 row. So that's an easy mistake to make. Again, even if you know what you're doing, I still do that all the time, where circuit's not working for some reason, and then you realize, oops, I was just off by 1 row. Fix that one. Okay, so let's run again. Okay, now our red is good, but something's wrong with our green. And it looks like everything's wired correctly, so I have everything in the same row there, but that's interesting. We have a color band on this resistor that's different from all the other ones. So these ones have a brown third band, and this one is yellow. And that's because I wasn't quite paying attention to my resistor color coding. This is 220 kiloohms instead of 220 ohms. So again, in Tinkercad, you can zoom in and you can click on it and it gives you the numerical value. In real life, resistors are tiny. It can be kind of hard to see the bands or tell the difference between colors that are really close to each other. And in this case, that's a big resistance, so it's getting like a tiny little bit of current through this LED, which is why it's dimmer than the others. But if I go ahead and change this back to 220 ohms instead of kiloohms, now I have fixed my green LED as well. So again, when you're handling resistors in real life, they're tiny, they're hard to see. You can always use a multimeter to check and measure the actual resistance if you are not sure of the value. So that is a good point to bring in the multimeter and talk about how that is also a useful debugging tool. So the multimeter in Tinkercad is much simpler than a real-life multimeter that's going to have more settings. This just lets you select current, voltage, and resistance. But for example, it is very useful to check your battery pack voltage. So this is something that I can't really simulate well. I can't simulate loose wires or dead batteries, but to confirm that your circuit is actually getting power, you would want to hook your multimeter up to your power buses. And in this case, I see that I am getting a little less than 6 volts because I am drawing some current through those LEDs, so the internal resistance of those batteries is causing a bit of voltage drop. But if it looks like all your wires are correct, but it still doesn't seem like your circuit is getting power somehow, could be dead batteries or a loose wire, so that's a good time to break out the multimeter and test that voltage. The other thing you can do, as I mentioned, is if you are having trouble reading color codes on a resistor, you can pull the resistor out of your circuit. Don't try to measure the resistance while it's in the circuit, and then connect those leads directly to the leads of the resistor. Switch over to the resistance. That's usually going to be an ohm symbol on a multimeter, and it'll tell you the resistance. Now, resistors usually have plus or minus 5% tolerance, so it's probably not going to be a perfect value like I get in the simulation here. But if you hate reading the color codes, that is a good way to check your resistor values, and then you can just pop them back in the circuit. So I've got 3 of my LEDs working now, but the yellow one is still not responding to this button press. And this one may be a little more subtle if you don't remember how these buttons are wired, which we went over back in the second video of this series. So the pins on this button are actually connected directly across here. These two are always connected to each other, regardless of whether or not the button is pressed. Pressing the button connects the pins on this side, so labeled 1A and 1B, over to 2A and 2B. So the way I have this wired here, the button is effectively just acting like a wire, so it's not doing anything. There's just always a closed circuit here. In order to have that done properly, I need to rotate the button like this. Now when I press the button, it's going to connect this row of the breadboard to this row of the breadboard. So I'm going to have to move this wire up here so it's connected to the button. Now when I run the simulation, you'll see that, as I expected, the other LEDs are always on, but the yellow LED only turns on when I press this button. Again, if you don't remember exactly how these buttons are wired, go back and watch the second video in this series where I go over that in more detail. All right, let's switch over to our third circuit, and this time we are involving a transistor and a potentiometer. This circuit is an LED dimmer, where I would expect that turning the potentiometer knob is going to dim the LED by adjusting the current through the resistor. I have the potentiometer cranked all the way, so the LED should just light up to full brightness when I turn the simulation on. Tinkercad is actually acting a little buggy at the moment and not letting me turn the potentiometer, so unfortunately I can't demonstrate that. But you can see that the LED is not lighting up at all, and I would expect it to be full brightness right now. So as usual, pause the video, look at the diagram, look at the breadboard, and see if you can figure out what is wrong here. So in case you couldn't find it, there are 2 things wrong here. The first is related to this ground symbol. Remember that This symbol does not necessarily literally mean that there is an external wire to ground, but we draw it to indicate that all of these parts of the circuit are connected to a common ground. Sometimes with big, messy circuit diagrams, that is just a little easier than drawing lines all over the diagram back to a single point. So it wouldn't be a big, huge deal to draw a line like that in this diagram, indicating that these are all connected, but in the absence of that line, it is implied that these points are all connected. And if you look carefully at the diagram, you see that I forgot to ground this one terminal of the potentiometer that is just dangling and not connected to anything, so that's the equivalent of leaving this connection out in the diagram. I need to remember to add a jumper wire over to the ground bus there. The second issue I have, if you look closely, and again, Tinkercad labels these pins for you. Collector, base, and emitter are the 3 pins of an NPN BJT. But in real life, those little C, B, and E letters aren't going to be printed on your transistor. You will need to first look up the circuit diagram and make sure you understand which pin is which, so C, B, E, and also look up the datasheet for the particular part you are using to make sure you know which physical pin is which on the transistor. So in this case, I happen to have mixed a couple of these up. This diagram shows that the collector should be connected to the cathode or negative end of the LED, so I have that correct. But the base should be connected to the 1 kilo ohm resistor, and the emitter should be connected to ground, and I have those two reversed, you see. So here is the base, I have that connected over to ground, and I have the emitter connected to the 1 kilo ohm resistor instead. So again, I have reversed those two connections. You have to be careful when working with transistors that you don't get the pins mixed up. So I am going to delete this wire. It should be this point that is connected to ground, and the base that is connected to this resistor. Now, when I run this simulation, I should see that my LED lights up. And again, Tinkercad isn't letting me turn this potentiometer for some reason right now, but when I turn this, I would expect that to dim the LED. Next, let's switch over to our op-amp circuit. So here we are using an integrated circuit in a dual inline package. We are building a non-inverting amplifier with the op-amp and feeding a signal from a function generator into the positive input. And based on the selection of resistors, we expect double that voltage on the output. So we should see an amplitude twice the amplitude of the input voltage from the function generator here on this output oscilloscope. Not shown, but implied in this diagram, we are also powering the op-amp with plus and minus 15 volts, which is coming from these two benchtop power supplies. I also have these multimeters hooked up, so they should read that plus and minus 15 volts. However, when I hit start simulation here, you see that I have just sort of made Tinkercad freeze. Nothing is happening. The function generator turns on. The oscilloscope sort of spazzes out. The power supplies and multimeters aren't working at all for some reason, and I'm actually making Tinkercad lag. It's not happy. It took a second to respond to the stop simulation button there. So in real life, again, Tinkercad doesn't always simulate short circuits or things exploding, but if I had built this on a physical circuit, something bad probably would have happened. Maybe I would have destroyed my op-amp or melted the breadboard or something. Who knows? So take a look. This is a pretty complicated one. Look at this diagram. Remember that you might need to go pull up the datasheet for the 741 op-amp and look at how those connections are supposed to go and figure out what is wrong with this circuit. All right, pause the video if you haven't already, because I am now going to explain 2 mistakes in this circuit. One, this might seem obvious now that I pointed out, but again, I have made this mistake myself when I was being careless. The op-amp is upside down. Technically, there's nothing wrong with doing this if you wire the rest of your circuit correspondingly, but usually the chip has a little notch or a dot to indicate the top, and the pins are labeled counterclockwise, starting with pin 1 in the top left, and that's how it's going to be oriented in the datasheet. So usually if you have the breadboard upright with the writing facing you like this, you're going to want that to match what you see in the datasheet and have this notch facing towards the top of the breadboard. I had wired everything assuming the chip was upright, but then put the op-amp in upside down, so that's just going to cause who knows what sort of mayhem as all of the pins are connected to the wrong things. However, we will see that just doing that did not totally fix my problem. I am not really seeing the output waveform that I would expect on the oscilloscope here. And if I check my multimeters, I see that I do have my 2 DC benchtop power supplies set to 15 volts, But the way I have everything wired, I would be expecting to measure 15 volts on this one and negative 15 volts on this one. And the way I wanted to set up two plus and minus split power supplies is to chain these together in series so they have a common ground in the middle, and then I get plus 15 volts out over here and negative 15 volts out over here. At least that is the intent. However, you can see that is not how I have them wired. I have them just wired independently to different buses on the breadboard, and I don't actually have them connected in series. So the way to do that, I need to get rid of this wire and think about this from left to right. Here I want plus 15 volts. I want this terminal to be 0 volts. So I'm going to wire that over to the positive terminal of this one, which is still 0 volts, but it is 15 volts higher than this terminal. Remember, voltage is relative between 2 points. So this one is going to give me negative 15 volts if I'm defining this middle point as ground or 0, which is what I have on my breadboard. So now when I run this, I have 15 volts over here and negative 15 volts over here. If you have a single benchtop power supply unit that gives you plus and minus 15 volts out, that could be not as much of an issue. But if you are chaining different power supplies together, you could also do this with batteries, for example, by putting two 9-volt batteries in series. Then you could have 0 plus and minus 9 volts. You got to remember to connect them in series like this. So some confusion with op amps, because normally a lot of the time you're just working with a circuit that has a single voltage supply and 0 and then a single positive voltage, so negative voltages can get kind of confusing. So in this case, I didn't have my power supply set up correctly, so even though I had my op amp wired correctly, it wasn't getting the power it needed. Now I fixed everything and I see I have a nice output. I have a 5-volt input, and based on the vertical scale here, I am getting a 10-volt output. Let's move on to our final example circuit, where we are using an L293D H-bridge and an Arduino Uno to control the speed and direction of a DC motor that is powered by an external battery pack. I have written some simple code such that when I run this simulation, it should just turn the motor on and spin it continuously in one direction. However, when I start this simulation, the motor does not spin. So I will zoom in a bit here so you can see the circuit. As usual, pause the video, and based on this circuit diagram, see if you can figure out what is wrong on the breadboard. So mistake number 1, and I mentioned in the previous video, this is probably the most common mistake I see students make when working with an H-bridge that has two different voltage supplies. So we have a 5-volt logic voltage from the Arduino and the 6-volt power voltage from this 4xAA battery pack. You need those voltages to have a common ground, but you do not want to connect them positive to positive or you will have a short circuit. And that is exactly what I have done here with this jumper wire on the breadboard. If I zoom out, you see I have 5 volts from the Arduino coming over to my power bus on the right side, and I have 6 volts from my battery pack coming over to the power bus on the left side. I do want those to have a common ground, so I want this black jumper wire here, but this red jumper wire is shorting my 5 volts to 6 volts, so I do not want that. I'm going to get rid of that. That will get rid of my short circuit. But we see when I start the simulation, my motor still does not spin because something else is wrong here. This is a case where you just have a lot of breadboard rows all right next to each other. And again, while I can zoom in really close in Tinkercad, in real life, it can just be easy to get these mixed up because these are only 1/10 of an inch apart. If I look carefully at my diagram, we see I have flipped a couple of the rows. So Arduino pin 4 is supposed to be connected to pin 2 on the H-bridge. Pin 2 should go to pin 7, and then you see the motor connections are inside there next to the ground pins. And if you look at this, I see I have those reversed. I have the Arduino connections coming in here closer to the ground pins, and the motor pins outside of that. So I'm going to go ahead and move those wires around, move these out here where they're supposed to be, again, looking at the diagram, and move the motor in to pins 3 and 6. Move this one, move this one. Now if I zoom out and run my simulation, I've fixed my connections, I've gotten rid of that short circuit, and I turn this on, and the motor spins as I expected. So there you go, 5 examples of circuit debugging. Now, to clarify, this is absolutely not an exhaustive list of things that can go wrong. There are plenty more things that can go wrong when building a circuit, including parts that are broken, which Tinkercad doesn't really simulate. For example, if you accidentally burn out an LED by using a resistor that is too small, or connecting it directly between power and ground with no resistor, you might not see any physical damage to the LED. Again, sometimes when you burn out a part, you'll be lucky enough to see a spark or smell smoke, and that will give you an indicator that something is broken. But many times, electronic parts, the same goes for things like transistors and integrated circuits. You won't really see or notice any physical damage, even if they are no longer functional. So if you have extra parts laying around, another option, something you can do, is just to swap in a replacement part and see if your circuit gets working. Again, I didn't really demonstrate that here since Tinkercad doesn't simulate broken parts. So hopefully this video series has given you some confidence in not only debugging circuits, but building them to begin with. Again, if you missed the earlier videos in this series on how to build these circuits based on the diagram, you can find those videos linked in the description below this one.